Hi students, we left off on this slide and we had just done SH2. So let's move on to C3H8, which is propane. So we were talking about how to put together a structure just by knowing what things like to do, so we don't have to go through a bunch of different structures that are incorrect before we hit on the correct one. So knowing what we know about carbon, we can go ahead and bond the carbons to each other because carbons like to bond to other carbons. And what we know about hydrogens is they like to be terminal, and they like to just have that one single bond. So we can put hydrogens all the way around our molecule like this, and magically we can see that we've used up 8 hydrogens, which is how many we have. Now looking at this molecule, you can see that everybody's happy. All the hydrogens are doing what they like to do. They have a single bond and no lone pairs, and all of the carbons are doing what they like to do. They have 4 bonding pairs. Also, all of the hydrogens have duets, and all of the carbons have octets. So we're good there, but we need to check and make sure we've used up the correct number of valence electrons. So we go ahead and we do atom and valence electrons. So we have 3 carbons and we've got 8 hydrogens. Now hydrogens, those bring 1 electron each. So we're going to go ahead and put 8 here because each hydrogen brings 1 electron and we've got 8 of them. And then carbons, right here we can see we're in group 14 or 4A. And let me erase that right there so we can see it a little bit more clearly. Group 14 or 4A. So we have 4 electrons from each of our carbons, and we've got 3 of those. So 4 times 3 is 12, and that gives us a total of 20. So if we go ahead and count up all of the electrons that we've used, we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So, ding, 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 we have a really good structure there. We've used up our 20 valence electrons. Everybody has an octet or a duet. And then the third rule that isn't as important as using up the exact number of valence electrons and the octet rule is that our atoms are doing what they like to do. So again, the first 2 rules, the octet rule and using the correct number of valence electrons, have to happen first. And then if the atoms can be in a position that they like to be in, that would be even better. Okay, so number 3 is Si2H6. So silicons behave like carbons. So we would probably go ahead and bond those together because we would bond carbons together because they like to bond to each other. Also, the only other thing we have there is hydrogens, and we know hydrogens don't like to be in between anybody. They like to be on the end, and they also only have a single bond. So we go ahead and distribute our hydrogens all the way around because nature likes symmetry, so we do that first. And just by looking at this molecule, you can see that all of your hydrogens have duets and your silicons have octets. So each of our hydrogens will be like that. It'll have its duet, and both of our silicons have 2, 4, 6, 8. You can draw the same circle around each of your silicons. So we're good with our octet rule there. But we need to add up our valence electrons and make sure that that number is right so we can make sure that we've got the correct structure. So we have 2 silicons and we have 6 hydrogens. Now, silicons are going to have the same number of valence electrons that carbons do because they are in the same group as our carbons right there. So group 14 or 4A means that we're going to have 4 valence electrons each, and we have 2 silicons, so 2 times 4 is 8. And then we have 6 hydrogens, and hydrogens always bring 1 valence electron. So we've got a 6 there, and 8 plus 6 is 14. And then we want to go ahead and count the number of electrons in the structure that we drew just to make sure we've got the right one. Okay, so we've got 2, 4, 6, 8, 10, 12, 14. Ding, 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 ding. We've got a good structure there. Everybody has an octet or a duet. We used up our 14 valence electrons, and our silicons are doing what they like to do, 4 bonding pairs, no lone pairs, and the hydrogens are doing what they like to do, a single bond and no lone pairs. So that brings us to Pi3. Now, phosphorus is going to behave like nitrogen because phosphorus is in the same column as nitrogen. So if we look back to what nitrogen likes to do, we can see that nitrogen likes to have 3 bonding pairs and 1 lone pair. And then we said that phosphorus likes to do what nitrogen does because it's in the same column. So again, 3 bonding pairs and 1 lone pair. So we drew NH3 on the other slide like this because nitrogen likes 3 bonding pairs and 1 lone pair. So let's go ahead and do the basic structure for Pi3 in the same fashion. Just because we know phosphorus likes to do what nitrogen does. And then if nitrogen likes a single lone pair, then phosphorus probably likes a lone pair too, like that, okay? Now we've got 3 halogens there. Remember, fluorine, chlorine, bromine, and iodine, those are halogens. And on this slide right here, we said that halogens like to be terminal, and we drew them terminal in Pi3, and they like to have a single bond and 3 lone pairs. So they like to look like that, or that, or that, which means that we're gonna need 3 lone pairs on each of these iodines if they're gonna be doing what they like to do. And remember, if this structure is wrong, that's okay, but we need to draw something. And we're just doing it in a shortcut version using what things like to do so we can get to the structure quicker, because oftentimes this will go ahead and give us the structure right away. Now let's go ahead and check this, and we'll add up our valence electrons, and we'll check to make sure everybody has an octet, because those are the 2 most important rules. So we have phosphorus, iodine, iodine, and iodine. And phosphorus is in group 15 or 5A. So it has 5 valence electrons. And iodines are halogens. Do you remember how many valence electrons halogens always have? They have 7. Okay, so group 17 or 7A, there's iodine right there. All of our halogens will have 7 valence electrons. So we've got 7, 7, 7, and 7, 7, and 7 is 21, plus 5 is 26. So we've got 26 valence electrons to work with. First, let's make sure that everybody has an octet, and then we'll count up those 26 valence electrons. So for iodine, you have 2, 4, 6 from the lone pairs, and then 8 from the bonding pair right there. And remember, if it's sharing those electrons, it still pretends that it owns them. So it can pretend it's got a whole octet. The same with this iodine right here, 2, 4, 6, 8. And the same with this iodine right there. So those all have octets, so we're good there. Now the phosphorus in the middle has 3 bonding pairs, so that's 2, 4, 6, and then a lone pair, which makes 8. And so we have an octet for phosphorus. So everybody has an octet, so that rule has been followed, and now we need to count up and make sure that we have 26 valence electrons. So let's just count around. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, and 26. Ding, 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 ding. Everybody has an octet. We've used up the exact number of valence electrons we had available. And the third, less important rule is that everybody's doing what they like to do. And again, if you got something wrong here, that's okay. Just draw another structure. And how do we know if it's wrong? If it's wrong, your valence electrons won't add up. Maybe we only used 24, or maybe you found that you used 28 or 30, or maybe somebody doesn't have an octet, they have a sextet, or maybe they've got 10 electrons around them. And so that'll tell you, oh, the structure's wrong, I've got to draw another one. Okay, so moving on to these structures. So we've got CH3OH. Now, we know that carbons like to be central. So we'll go ahead and draw the carbon there. And then this right here, what we'll notice is that the hydrogens are in different spots. They're split up, and that's on purpose because CH3OH is drawn in the condensed format, and it's giving you a clue to the structure. So it's saying what you have first is a CH3 unit. So that's CH3, and then what comes next is O and H. Now just look at the structure and try to spot what's not right about it right now. So we can see that each of our hydrogens is terminal. They're all on the end, and they all have a single bond. None of them have a lone pair, so those are all happy. The carbon there, the carbon is surrounded by 4 bonding pairs. So we've got 4 single bonds. That's 4 bonding pairs. 2, 4, 6, 8. That's an octet. The oxygen, it is surrounded by 2 bonding pairs, 2 single bonds. So it has 2, 4 electrons around it. So it only has a quartet. So that's a problem there. It needs to have an octet. Now, if we tried to fix that by putting a triple bond there and saying, okay, now oxygen has an octet because that triple bond is 2, 4, 6, and the single bond on the other side is 8, so it has an octet. What do you notice is wrong now? Yeah, that carbon has way too many. It would have 2, 4, 6, 8, 10, 12 around it. So we know that's not right. So we want to erase that. So we want to go back and get rid of that triple bond there. Now think back to what oxygens like to do. Oxygens like to have 2 bonding pairs and 2 lone pairs. And there's a couple of different ways they can do that. One is with 2 single bonds and 2 lone pairs, and the other way is with a double bond and 2 lone pairs. Now we already know in the structure that we're doing that the oxygen has 2 single bonds. So it doesn't have the double bond example. So what we probably need is what? you're right, 2 lone pairs. Okay, so now oxygen has an octet. So just looking at this molecule, we can see that everybody's happy. Our hydrogens, those all have their duets. And our carbon, 2, 4, 6, 8, it has its octet. And the oxygen, 2, 4, 6, 8, it has its octet. Now let's go back and check and make sure that we have the correct number of valence electrons. So we can already see that everything's doing what it likes to do and everybody has a duet or an octet, but we have to check. So each carbon brings 4 valence electrons, and we would see that on the periodic table up here. It's in group 14 or 4A. Each oxygen brings 6, and that's up here, group 16 or 6A. And then each hydrogen brings how many? 1, you're right. So that's group 1 or 1A right there. We have 4 of those, so 4 times 1 is 4. Now 4 plus 6 is 10, plus 4 is 14. So the first 2 rules, the most important rules we have to follow is we have to have exactly 14 electrons showing up in this structure, and everybody has to follow the octet rule. And then the third rule, which likes to happen but doesn't always happen, is that things need to do what they like to do. Now let's go ahead and count up, make sure we have 14. We have 2, 4, 6, 8, 10, 12, 14. Ding, 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 ding. So we have the correct structure there. Okay, moving on to C2H2. So who likes to bond to who here? Carbon likes to bond to carbon. So we'll just go ahead and make carbon bond to carbon there. Now we only have 2 hydrogens. So let's just go ahead and put 1 hydrogen on each side because again, nature likes symmetry. And then we're going to look at the structure and we're going to go, there's something wrong there. The hydrogens are happy, but those carbons only have 1 single bond on each side of them, so that's a quartet. So we have to figure out how are we going to solve this? What would make that right? Well, let's just try something. What if we made this a double bond? Then how many valence electrons would the carbons have around them? Well, you guys can count up 2, 4, 6, because there's 4 from the double bond and there's 1 from the bond between the carbon and the hydrogen. So 2, 4, 6. So that wouldn't work. So do you have another guess? How about a triple bond in there? So we'll just put 2 more electrons in there. We'll put the third part of the triple bond. Now, does that give each carbon an octet? So from the triple bond, we have 2, 4, 6, and from the bond between the hydrogen and the carbon, we have 8. So each of our hydrogens has a duet, and each of our carbons has an octet. So let's add up our valence electrons and see if that's correct. So each hydrogen brings 1 valence electron, and we've got 2 of those, so we've got a 2 here. And each carbon brings 4 valence electrons, and we've got 2 of them, so that's 8. So we have a total of 10. So let's go ahead and count them up. So we have 2, 4, 6, 8 from the triple bond, and then 10. Ding, 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 ding. Okay, so if we were to back up and we were to do it the way that we did it in the beginning, where we added up all the valence electrons, and then we tried to make a structure that way, what we would do is we would go ahead and draw this structure, and then we would see that we've used up 2, 4, 6 of our 10 electrons, and then we would know that we had 4 left over. And the rule said that you have to take any of your leftover electrons and you distribute them to the terminal atoms, which would be the hydrogens, except when they are who? Hydrogen, because hydrogens don't like lone pairs. No lone pairs and just a single bond. And the rule after that said when you're done there, go ahead and distribute those lone pairs to the central atoms. We have 2 central atoms here, so we'd go ahead and put the lone pairs here. Now, we're not done because we can see that each of our carbons has a sextet. It has 4 electrons that are bonding, so those 2 single bonds there, we have 2, 4, and then 2 from the lone pairs, which is 6. So we still don't have a happy molecule here because the carbons don't have octets. So the left carbon says to the right carbon, hey, I don't have an octet, so you need to share those lone pair electrons. So this carbon's like, okay, and it throws them down in there and it makes the second part of the double bond right here. And then the carbon on the left is like, yay, I have an octet now. Oops, I just erased that whole thing and I am so sorry, but I will draw it again. Here we go. So this is where we were. Okay, so we have a carbon on this side that has an octet, and we have a carbon on this side that has what? A sextet. You're right, because you have 4 from the double bond and you have 2 from the single bond, and that's 2, 4, 6. So the carbon on the right is not happy. It says to the carbon on the left, hey, I shared my electrons with you to give you an octet, and I still don't have an octet. And the rule is that I have to have an octet. So you need to share your electrons with me. And the carbon on the left says, okay, I can do that because I'm a carbon and I don't like lone pairs anyways. That's probably in the rules somewhere. So it throws its lone pair electrons in the middle right there, and it turns them from non-bonding electrons into bonding electrons. And what we have is a triple bond between those 2 carbons right there. And remember, we had 10 valence electrons that we had to use, and now we need to make sure that we're following the first 2 rules, which is that we have an octet or a duet for everybody, which again we do. Duets for our hydrogens. 2, 4, 6, 8, octet for that carbon. 2, 4, 6, 8, octet for that carbon. And we need to add up and make sure that we have 10. So we have 2, 4, 6, 8, 10. Ding, 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 ding. The structure looks like this. And that is our simplest alkyne, which is a hydrocarbon with a triple bond. And that is called ethyne or acetylene. All right, number 7, BF3. So this one is a special one because we've got boron. Now, if we look back at the rules, we can see that boron is special because it likes a sextet. It doesn't want to have an octet like everybody else. So if BH3 looks like this, then BF3 will probably have a very similar setup. So let's go ahead and do BF3 here. So we can draw B and then put F on top, and then F and F here. And then if we had hydrogens in place of the fluorines, that would be the complete structure because the hydrogens would have duets and the boron would have a sextet. But we have fluorines there, and fluorines are halogens. And remember, halogens like to have a single bond, and they like to have 3 lone pairs. So it's going to look like this, this, or this. So we have to go ahead and draw those lone pairs in. So all right, our boron in the center, it has a sextet. If you count around those single bonds, you got 2, 4, 6. And it's happy. The fluorines, they have a single bond and 3 lone pairs. So that's 2, 4, 6 from the lone pairs. And the single bond makes 8. 2, 4, 6, 8. And 2, 4, 6, 8. So we're following the octet rule here. Now we need to make sure we use up the proper number of valence electrons. So we have boron, and boron is right here. It's in group 13 or 3A. So it has how many valence electrons? 3, that's right. Fluorine is a halogen. Halogens always have how many valence electrons? 7. It's in group 17 or 7A. We have 3 of them. If we have 3 and they're 7 each, that's 7 plus 7 plus 7. So that's 21. So we have 24 valence electrons total. All right, so let's count these up. We've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Ding, 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 ding. We've got a winner there. So BF3, you can also draw it like that if you prefer. But that's a winning structure on BF3. Okay, last one on this slide. CCl2O. Let's figure this one out. Okay, we have a carbon, we have 2 chlorines, and we have an oxygen. Now what we said about carbon is that it likes to be central. So let's just go ahead and draw it central. So we've taken care of the carbon, and then we have 2 chlorines. And remember, the chlorines aren't going to want to bond to each other if at all possible. And the carbon likes to be central. So let's just go ahead and put the chlorines on each side of the carbon. And then we have oxygen. And we could bond oxygen over here, but let's go back and remember what we just said about chlorine. Chlorines are halogens and they like to be terminal, which means they like to be on the end. They don't like to be between 2 things. So that's probably not where the oxygen's gonna go. So let's go ahead and take that off. And we know that carbon likes to be central, so let's go ahead and put the oxygen up there. Now looking at this thing, we can go, we know that there's going to be some lone pairs in there, and we can see that that carbon only has a sextet, and we can see that the oxygen's not happy and it doesn't have an octet. But what on earth do we do with this? Well, if you're stuck at this point, you can start to draw some bonds in and draw some lone pairs based on what things like to do. Or you can revert back to adding up the valence electrons and following the rules. Either way is fine. And there's no right way to do it. As long as you're getting to the correct answers, the way that your brain works to do this is fine. And again, you guys, you're going to have to draw and erase a few structures to get to the right structure sometimes. So carbon likes to have, it brings 4 valence electrons, oxygen 6, and chlorines are halogens. And halogens always have how many valence electrons? 7, that's right. So we have 4 plus 6, which is 10, plus 7, which is 17, plus another 7, which gives us what? 24, that's right. Okay, so if we're using the rules, what it said is go ahead and bond things to a central atom and then distribute any leftover electrons to the terminal atoms. So we've used up in our structure 6 electrons so far from those 3 single bonds, 2, 4, 6. The rules say go ahead and distribute, so 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, so we've used up 24 valence electrons, but is there a problem with our structure? Yes. The chlorines on each side, those have a single bond and they have 3 lone pairs. So that gives them an octet, and they're doing what they like to do. So the problem probably is not the chlorines. So let's look in the center. That carbon only has a sextet, so you can see 3 single bonds around it, which is 2, 4, 6. The oxygen, it has a single bond in 3 lone pairs. So the 3 lone pairs make up 6 electrons, and that single bond has 2 electrons, so it makes 8 electrons to give that oxygen an octet. But the carbon doesn't have an octet, and the oxygen is not doing what it likes to do. So we have to satisfy the octet rule for the carbon, and we're probably going to be asking the oxygen to share some electrons because the oxygen is not doing what it likes to do. And if we ask the oxygen to share some of its electrons, we might get it to do what it prefers to do. So the carbon says, hey, oxygen, you're hogging up a lot of electrons up there, and I don't even have an octet. And the octet rule is one of the basic rules of the universe, so you need to share with me. And the oxygen's like, okay, I can do that. I don't like to have 3 lone pairs anyways. I like to have 2 bonding pairs and 2 lone pairs. So it throws a couple of its non-bonding electrons next to that single bond there, and it turns that into the second half of the double bond. Come on, eraser. Okay, there we go. And then what we would have is this right here. Now I'm going to take those electrons on the top of the oxygen, and I'm just going to move them over to the right side because that's the way you'll see them drawn most often. So let me just go ahead and move them over here. It doesn't really matter. You could leave them on the top if you want, but we're going to move them over there. All right, now what we see is that the chlorines have an octet, and they're doing what they like to do, single bond and 3 lone pairs, so they're happy. And we can see that carbon has an octet, 2, 4, 6, 8, and it's doing what it likes to do. It has 4 bonding pairs and no lone pairs. And oxygen has an octet also, 2, 4, 6, 8, and it's also doing what it likes to do, 2 bonding pairs and 2 lone pairs. So if we look back here, we can see that we've seen that before in that molecule right there, formaldehyde. Oxygen's got 2 bonding pairs from that double bond there in 2 lone pairs. So coming back here, everybody's got an octet, And we want to make sure, again, that we've got our 24 valence electrons. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Oh, where did I mess up? Okay. 2, 4, 6, 8, 10, 12, 14, 16. Oh, I counted that bond again. Okay. Scratch that out. 18, 20, 22, 24. Okay, learn how to count electrons, Professor Gray. You don't count one of the single bonds 2 times. Okay, so we used up 24 valence electrons there. See, I've been doing this for over 2 decades and I still occasionally make mistakes, so that's okay. We just go ahead and correct it and we learn. Okay, so everybody has an octet. Everybody, or excuse me, the whole molecule is using up 24 valence electrons. Those are the 2 most important rules. And then the third one, everybody's doing what they like to do. So this is awesome sauce. Okay, so we've got another couple of slides of molecules to practice with Lewis structures, but I'm gonna wait until the next video because the bigger videos take a really long time to upload. All right, you guys, until next time, have a good evening and I will see you tomorrow.